So good evening, welcome to LinkedIn. So before we get started, I'd like to introduce myself and my co-presenter. So my name is Aditya. I work on the Kafka engineering team at LinkedIn, along with Dong, who also works with me. So we're talking today about a brand new feature in O9 Kafka called Quotas. Quotas are basically the ability to define throughput thresholds for any of your clients, for producers and consumers specifically. So let's talk about motivation for building this feature, and let's see why this is important. We operate our clusters as multi-tenant clusters, right? So there are hundreds of clients connecting to our clusters. So in a multi-tenant environment, all resources are shared: CPU, disk, network. A single bad client or a handful of bad clients can hurt everyone. So what are examples of bad clients? So let's take a buggy client, right? A badly implemented producer, or a producer that's producing, like a very bursty producer, for example, that can push a lot of data into the cluster in a very short period of time. Some clients aren't even bad, like bootstrapping consumers. Let's say a client consumer group starts consuming from a topic that has a lot of data, and it doesn't have any offset. So this will basically bootstrap and consume a lot of system resources in a short span of time. So basically, we need a way to provide better QoS for well-behaved clients. So preserve throughput and latency for the others, at least not let it get affected badly. In addition, what you can also do with Quotas is establish API limits for your applications, right? If you are running these clusters as a service and you want to, at the end of the month, send somebody a bill based on how much they've used the cluster, you can actually use this. So what quantity do we throttle on? Right, so quotas in Kafka are enforced per client ID. So client ID is this thing we set on all producers and consumers when instantiating them. This is used to logically identify an application. So a simple example would be all your consumers in a consumer group would have the same client ID. So this is why we basically chose client ID. Right, it makes sense. You know who the request is coming from, and we basically define a quota on top of that. We could have also defined quotas on other dimensions. Let's talk about why we didn't do that. So we didn't do any quotas per topic, specifically because topics are typically multi-tenant. There is no clearly defined notion of owner of a topic, and like you really don't want clients of a topic, well-behaved clients of a topic, to get throttled because you have one badly behaved client, right? You have one bootstrapping consumer, for example. Similarly, we didn't have quotas per client ID and topic combination because there are some nuances there that I won't get into right now. So the way it works is basically you are allocated a blanket quota for produce and fetch across your entire cluster for every single client ID. All of them get the same quota. This ideally should be set to some not a very high value initial, not a very high value. So this is basically everybody gets this dedicated to them. But there are always some clients that justify higher quotas, right? I mean, let's say you have a producer application that is allocated 10 megabytes per second in your cluster. That's the default, for example. And there are certain clients, like the 10%, like the heaviest 10%, that need much higher quotas than this, right? So the answer is not to basically have a higher default quota for everyone. The answer is the ability to specify overrides. So how do we do these overrides? Overrides need to be handled dynamically. So we store these overrides in Zookeeper because rolling bounces take too long. They require too much effort. Every time we had to change quota for someone, if we had to bounce our clusters, our SRE would be very unhappy. So basically, we have tooling that will basically store these overrides in ZK. Brokers parse these notifications and apply the quota immediately. So this is effective like within a few seconds after you basically changed your quota. This is what it looks like in Zookeeper. You have the config znode. The client quotas are stored under config, very, very similar to the way we do topic-based overrides currently. So this is an example of what a quota would look like, right? Producer byte rate for your client ID would be 1 meg per second in this case, and your consumer byte rate is the same. For the same client ID, it's a 1 megabyte per second. So let's talk about how we actually manage these quotas in the cluster. So in order to throttle anything, you need metrics. You need to measure what you're throttling, right? You need to measure the byte rate for each client ID. So on each broker, we have metrics for each client ID that is connected to your cluster. However, client IDs can come and go, and we don't need to retain these metrics forever. So basically, we keep these metrics for a short period of time until your client is actively connected. Otherwise, we get rid of them, and they're recreated once the client comes back. So what these metrics track are basically byte rate for the client. So over the last 10 seconds, 20 seconds, 30 seconds, I mean, it's a configurable window. What was the throughput that your client actually generated? So the entire goal of Quotas is once you detect that some client has a throughput that's higher than the allocated quota, we have to basically bring them to their quota, right? At or under the quota. So the goal here is to basically reduce the client throughput to a desired rate. So the way we do this is to basically insert delays in the responses that we send to clients. Let's say you have a produce request or a fetch request. What ends up happening is your requests get slowed down. I'll get into details in how that actually works, but the key idea here is that small violations result in smaller delays. So we have small measurement windows, like 10 seconds, I think is the default. So for these smaller measurement windows, we track your byte rate. If we detect that you've exceeded your quota, a delay will be applied. So the reason we use very small measurement windows is to avoid long pauses. So if you had like a 5-minute measurement window and at the end of 4 minutes we detect that you exceeded your quota, there'd be a big long pause on your responses. And that's like pretty bad user experience, and we wanted to avoid that. And of course, the way this is returned to clients is basically not in terms of an error, but client-side metrics are available to detect throttling. So this is how we calculate the delays that we insert in the responses. So if W is the window size that we measure over, and mu is the observed rate, and Q is the quota, so the delay that is inserted is equal to that formula there. It's W times the delta in the observed and the desired rate divided by the observed rate. The goal is that the end of the delay, the throughput of the client should be equal to the quota, which is what this gives us. So let's just look at how enforcement works with the simple example. Let's say we have a producer that's sending a request to a broker. The request channel sends the request to the replica manager. In case of producer, the request is actually appended to the log. Once the request is appended to the log, we track how many bytes were appended to the log and record that into a new module called the quota manager. So what the quota manager does is it tracks your byte rate and it uses that formula to compute a delay. So once you basically, if your delay is 0, obviously, which should be the case for most clients, a response is sent back to the producer. So this is the way, this is normal operation, right? This is how things work right now. But if your throughput has exceeded the quota and a non-zero delay has been calculated, your response is put in a delay queue before it is sent out. And basically, we have a Reaper thread where at the end of your delay, or once your delay expires, we send the response back to the producer. So it basically delays your response. It works very similarly for consumers: request, process, fetch offsets from the log, record metric, delay, DQ, and return. So the reason we basically append to the log in case of producer before we apply the delays, because we don't actually want to buffer the requests in memory. I mean, if there's a lot of requests, that's a lot of memory that gets spent in, that's a lot of requests that can get throttled and occupy a lot of memory. So we actually become pretty efficient with respect to memory usage. The same way for consumers, the data isn't really read until it's time to send a response via zero copy. So even in this case, we aren't actually maintaining the offsets in memory, the actual records in memory. So far, I've just spoken about implementing slowdowns. I guess another way to do it would have just been to return an error, right? I mean, we detect a quota violation, I return an error, client retries. That's like the most typical way to do it, I suppose. So why didn't we do it that way? I think the answer is that I mean, error handling can be hard. It's hard to trust client implementations to always do the right thing, right? It's tricky to implement back off. It's tricky to implement retries. And very often, if you get these wrong, you'll end up exacerbating the same problem you're trying to solve in the first place. So we needed something easier that'll work for all clients. You don't need to rewrite your client implementations. This will just slow your request down and you get a response. So let's talk about how we get started with using this feature. So if you check out O9 and get started and want to use this, all you have to do is basically set 2 configs on your broker, right? You have your default producer quota and you have your default consumer quota. I'd like to call out that these quotas are configured per broker within your cluster. So there is no mechanism currently to share quota usage across different brokers for a client ID. This is how you apply overrides. There's basically tools that are provided to you that will go and it's pretty self-explanatory. So 2 configs, tools to do overrides. As far as monitoring is concerned, we have a bunch of metrics on all the common clients. We have the producer, we have consumer metrics, old consumer, new consumer also. So we basically, what these metrics show you is how long your clients were throttled. So since no error is returned, the clients really don't take action. It just works out of the box for them, but it is a useful mechanism to actually tell someone that their requests are getting delayed and they actually need to cut down on their byte rate or actually talk to us about getting overrides. On the broker, we have a few metrics per client ID also, which is basically byte rate and the average throttle time for client ID. Byte rate is basically the same metric that's used for enforcement. So you can look at it via JMX also, and it's nice. Zookeeper and old consumer metrics are also supported. So let's spend a couple of minutes talking about the rollout strategy. So how at LinkedIn are we actually rolling these quotas out? So what we really want to do is to avoid a scenario where the quotas are way too high and thus not really that useful, or they're way too low and everybody ends up getting throttled and angry at us, right? So what we want to do is basically, our first rollout is going to be to basically deploy without enforcement, right? You get the metrics per client ID on the brokers for free now whenever you deploy, but we don't set the quota. By default, it is unlimited, right? So you can actually look at these metrics to track throughput for all client IDs. You look at the distribution, you can actually find a reasonable default, right? I mean, you have 1,000 clients, you know where to draw the line. And then what this also gives you is the ability to now identify candidates for overrides. Now you can actually track who is consuming what fraction of a cluster's capacity. And you can actually say if certain clients deserve higher quota or not. If they don't deserve higher quota, then you don't give them an override, otherwise you do. Also, I think the trick is to, when in doubt, to start with a slightly higher threshold. Again, to simply avoid the case where you end up throttling everyone, and it just creates a lot of problems for all your clients. So the next piece, I think we'll talk about evaluation, talk about functionality and performance. So Dong is going to talk about this. Thanks.
Hi. So now that the quota has been implemented, we want to make sure that quota actually works. By saying it works, we actually mean 2 parts. First, we want to make sure that quota actually enforces guarantee. That is, the throughput of producer and consumer are limited by their respective quota. And second, we also want to make sure that it improves small clients' performance. Because while quota's direct goal is to limit clients' performance, its ultimate goal is to improve the client's performance. So we'll evaluate into these 2 parts. Okay, so in the first scenario, we set up a small Kafka cluster of 4 physical machines, and we run brokers on these machines. And we give the Kafka broker different quota configuration, and we run multiple producers and consumers with the same client ID. And we measure the throughput on these brokers. In the first scenario, there's no quota limit. That is, we set a very large quota limit. And we observe that the producer, with this physical setup, the producer achieves roughly 90 megabytes per second throughput. The consumer achieves roughly 100 megabytes throughput. Okay? And next, we give a quota limit of 50 megabytes per second for producer and consumer traffic, respectively, since we are using the same client ID for all the clients. The broker's limit, the broker's throughput should be limited by quota. And in this case, we do validate that the producer and the consumer throughput are close to 50 megabytes per second. To further validate the quota, we again set the quota limit to be 10 megabytes per second. And we show that the producer and consumer throughput are again close to 10 megabytes per second. Okay, next, we want to validate that how quota can improve client's performance. We separate these into two parts, the producer and consumer. For producer, we are mostly interested in the latency because we can control the throughput. And because consumer will always consume at higher throughputs, assuming there's enough message, we will evaluate the throughput performance improvement for consumer. First, suppose that initially there's a very small client that is running alone in the cluster. It happily enjoys all the bandwidth resource. And later, a cluster of other clients join. They have very high throughput demand. For example, join the Bootstrap. And these clients will take away some bandwidth resource and CPU resource. The initial small client will be unhappy because it can't enjoy the little throughput it wants. And with the help of quota, we actually separate the throughput, we limit the throughput consumption by that cluster of new clients, and the initial client hopefully can be happy. What we want to compare is between the right side two scenarios. We tag it as the together and the quota, and we tag the initial scenario as alone in the evaluation. So here's the evaluation. In the first scenario, to improve performance improvement for producer, the producer runs at, let's say, 2 megabytes per second. That is configurable. And after some time, later, we start a cluster of other producers that tries to take away the bandwidth resource. We show that the latency for this small producer will spike from 1.5 milliseconds per message up to 23 milliseconds per message. That is more than 10 times higher. And you can also see in this graph how the latency changes over time. And with the help of quota, let's say we give the quota of 10 megabytes per client ID. In this case, the small producer will have a latency of 2.5 milliseconds. That is much better and very close to its original latency. This does show that with the help of quota in a multi-tenancy environment, the small producer can enjoy its low latency. That is very useful. And in this part, we want to evaluate performance improvement for small consumer. How we do that? First, let's say we have a consumer that is running alone. We assume that there's enough message that is available for consumption. Initially, because the consumer doesn't have quota, with all the physical resource, it can consume with a roughly 19 megabytes per second throughput. For fair comparison, we give it a quota of 50 megabytes. And then in this case, the throughput is 45 megabytes per second on average. Then I start a cluster, a bunch of other consumers that tries to consume as much throughput as possible. The throughput of the initial consumer drops to 31 megabytes per second. That is roughly 1/3 of the 33% drop. And with the help of quota, let's say I give a quota of 50 megabytes per second for each client ID. And in this case, I assume that the initial client have its own client ID, and a bunch of other consumers enjoying another unique client ID. With these two client IDs, we show that the throughput for that initial consumer will increase from 31 to 40 megabytes per second. That is roughly 33% increase. This shows that how quota can help the throughput of consumer. So to summarize, our evaluation results shows that the quota's functionality is actually enforced. And quota can actually help the performance of the small producer and consumer. Okay, so here's a rough idea of what can be done in the future for quota in Kafka. First, currently, we only throttle the traffic between client and broker. That makes sense in most cases, but another use case is, suppose you run Kafka in a shared cluster, and during its bootstrap, even the inter-broker traffic can take a lot of bandwidth resource. And because it's a shared cluster, you want to limit the performance impact on the other applications. That's when you may want to throttle the replica traffic. And currently, we only throttle the fetch request and produce request. But in the future, some other request type, for example, the offset commit request, may carry arbitrary metadata. And a bucket client may consume too much resource with this request type. That is why you may want to throttle such request type as well. And another interesting use case is for how Quota can work with authorization. Imagine that the motivation for Quota is to run, for example, in a multi-tenancy environment where a lot of organizations will share the same cluster resource, and we want to make sure that they properly share the resource. And for Quota to run correctly, you want to ensure that the client ID is set correctly for each consumer and producer. And so that, for example, you may charge these clients based on the number of resources they consume. But if you are not able to authenticate that they are using the client ID they own, the Quota is not guaranteed to work properly. But with current authorization, to my best knowledge, current authorization authorizes that you own the principal and authorize what action you can perform. But it doesn't authorize that you own this client ID. In the future, I imagine that we may want to bind the principal to the client ID to make sure that they actually use the client ID that they own. Okay, that's all the future work. And now I think Adi and I will answer your questions.
I have a question. So for the byte rate quota, is it enforced on each broker or is it enforced on the whole cluster of?
So it's enforced on each broker right now. So to enforce it across the entire cluster would actually require them to share their metrics amongst each other. Yeah, that is actually, we didn't tackle that problem. We didn't actually think even it was necessary to tackle that.
Yeah, I think the problem is if you have uneven distribution of partitions on the brokers, some brokers have more partitions than the others, and it's naturally they will get more traffic.
Yeah.
So in that case,
so we actually try to do a fairly good job at balancing traffic across, balancing our partitions across the entire cluster. I think another way to also look at it is that effectively your quota is like operating a one node cluster, right? Essentially. So, I mean, regardless of the way partitions are distributed, your broker can only tolerate a certain amount of traffic. I mean, just because your partitions are unevenly distributed doesn't mean that you should actually sign up for more traffic than you can tolerate. Okay. So I think of it as just operating a one node cluster.
Okay. Another question is, I think for the producer API, it's asynchronous. So you send the data and you don't have to actually wait for a response. So in that case, if you delay the response to the producer, what happens? What actually happens at the client side? Does the producer eventually start to drop messages to produce, or?
So basically you have a max in-flight requests on your producer, right? So once you actually have that many, once it's actually set to a reasonable value, like a few, once you actually reach those many requests, I think you can configure this on the producer. So for example, you can block new events when you set block on buffer full. Okay. So yeah, in that case, I don't think you'll lose data. You'll probably start getting errors. I see. And I would highly encourage, if no data loss is super important, then you should probably use the callbacks or the synchronous APIs, the ones that return the futures. Right.
Okay.
I have a follow-up question on number of bytes. Is it when the topic is compressed, is it compressed number of byte rate or uncompressed?
I think it's the amount of data that gets appended to disk. I think it is the compressed byte rate.
Oh, okay. And regarding your client ID, is it on the producer side? Is it per host, or is it because there is no notion of group on the producer side?
Yeah, so it's basically your client ID. So if you have an application with 10 producers, like running on 10 instances, you should probably set them to the same client ID. So it's not managed as a group, but it's basically an identifier for your client.
Host.
Not for your host, for your producer instance or a group of producer instances. So you can have multiple producer instances with the same client ID.
So the client is responsible for generating the client ID, is it? How's the...
You can set the client ID on the producers.
Okay. And follow-up question about Quota is, suppose my goal is to, I have infinite capacity of storage, but my problem is network bandwidth. So why not drop all the data is going to be dropped anyway, right? That when you exceed the limit, the quota limit, why not drop it at the producer side? Why drop it so late on the broker side?
Yeah, but I mean, dropping data is a very contentious thing, right? I mean, basically, it really depends on what your client implementation does. I think most people, if dropping data is not acceptable, they will probably end up retrying. So I don't think you can. Yes, I didn't understand the question fully.
What I'm trying to say is, suppose producer instance exceeds the bandwidth or quota limit. Let's say 1 megabytes per limit. And a producer is producing 10 megabytes per minute. I mean, you're going to drop that to 9 megabytes, right? So my goal is I have infinite capacity. Storage engine. I don't care about the storage. I care about network saturation. So let's suppose you have LinkedIn running and you have, let's say, logger. You produce tons of debug logs, events. You want to, let's say you have log topics, very, very traffic heavy. So how do you, I mean, basically you have infinite capacity. Just want to protect the network saturation.
So, I mean, this does kind of protect against network saturation, right?
No. So the 9 megabytes is going to travel over the network and you're going to drop it at server side. I'm saying drop it up front.
Yeah, but to know that you're getting throttled, you would have to send the request to the broker anywhere, right? Regardless. So that...
Yeah, but then you don't have to... the data doesn't have to travel, just the request.
Yeah, so we haven't actually thought about that. That's not an issue for us at this time, so we haven't thought about it.
Okay, no problem.
Yeah.
Okay, thanks.
Go ahead and save any more questions.
Okay, thanks.
No question?
Yeah, we'll save them for after the end, and we'll go ahead and move on to Joel now.